Hello and welcome everyone to our AI tutorial. In our previous video we have discussed about BFS, which is breadth first search, and in this video we'll discuss about the DFS, which is depth first search. So BFS and DFS both are searching algorithm, and in terms of BFS we got to know about the fringe and simulation, and in terms of DFS we will also discuss about the fringe and the simulation, and also the completeness and optimality, also space complexity and time complexity. So suppose this is a particular state space tree. So in this state space tree you can see that A is the start node and G is the goal node, and A is in the level 0, level 1, level 2 and level 3. And we all know that in terms of DFS, we implement DFS in a data structure called stack. So we will be implementing DFS in stack data structure. There is another technique to implement or to simulate DFS, which is backtracking or recursion. But for the sake of simplicity, we will be using stack or LIFO as a fringe. So in this state space tree, we can see that A has three children, B, C, D. B has children E and F, and C has children K and H. D has children, and A is the parent of B, C and D. This is how we define a state space tree. So now we will see the simulation of DFS. So we will now simulate this state space tree in DFS. So first we will expand A node, and here we have two children, which is B and C. So last in, first out. Last is C, LIFO. I'm again writing it. Last in, first out. So yeah, first out, last in, first out is B. We will expand B. So B has two children. One is E and D. So now we will expand B. D has children's H and I. So C, E, I would be the last one. Okay, now we will expand H because H is the last element in the fringe. So we will expand H. We have C, E, I into the fringe. H doesn't have any children, so we will expand I now. So I also doesn't have any children, so we will expand C. We will expand E now. So E has children's. E has children's. I think it's G and J. Let's see again. Yeah, it's G and J. C, J and G. Now we will expand J, and lastly we will expand G. So what is the path? Here in this DFS, what are the paths? We will write the paths. So the paths are A, B, D, H, then it's I, then it's E, then it's J, and lastly it's G, or the goal node. Now let's see the graph or the tree, state space tree. So here you can see like this A, like this A, B, D, H, or the path is going this way. So this is the way. Okay, so in DFS what happens is whenever in DFS searching algorithm, it will search towards its depth. That's why the time complexity is big O of B D plus 1. D is the depth and B is the branching factor. Okay, and the space complexity is big O of B and M. B is the branching factor and M is the max depth. So BM is the space complexity, and it is a linear space complexity. This is linear. This is a linear space complexity, linear. So just remember this, like BFS has a exponential space complexity, but DFS has linear space complexity, which is a very big difference in terms of BFS and DFS. So here I have written already the B is branching factor and M is maximum depth, and now D is the depth. D is actually nothing but the depth in the time complexity. This is the time complexity, which is big O of B D plus 1. So now we will discuss about the completeness and optimality, which I have written over here, completeness and optimality. DFS is neither optimal nor complete. BFS is neither optimal nor complete. I'm writing it down. I'm so sorry, it's DFS. DFS is neither optimal nor complete. Now we will see why DFS is neither optimal nor complete. I'm literally sorry, I first said BFS, but it's DFS. DFS means depth first search is neither optimal nor complete. BFS is complete and optimal. So how we identify that BFS is complete and optimal and DFS is not complete and optimal? So now we will write. So I have written it like in terms of BFS, step cost is same, and in terms of DFS, step cost is high. So this is how we define the optimality issue. Actually, what is the step cost? Like in terms of formal definition, whenever we will write a formal definition of the BFS and DFS, why BFS is optimal, we will write that all step cost is same in terms of BFS, but in terms of DFS, if it is a infinite loop, then infinite or a graph, what happened is like all step cost is not same, it's quite higher. reaching out all step is higher than the BFS. So that's why DFS is not optimal. So actually for the formal definition we would use that, but for understanding, for explanation and for demonstration, I will explain it in another way, another manner. So let's draw another tree, status space tree or graph, whatever you say. So yeah, let's draw another. So in terms of DFS, what happens is, like, in terms of DFS, it will return you a suboptimal goal, because how DFS is actually moving, DFS will go to the A node, then B node, then D node, then H node, and then D node. It will get the leaf node first, which is the suboptimal goal, because here you can see in level 2, level 0, let's say it's level 0 and it's level 1, and it's the level 2. We have another goal in level 2. Okay, so this is more optimal than this. Yeah, but DFS will return you back this suboptimal goal, which is G2. G2 is the suboptimal goal. Because of this issue, because DFS has a tendency to return you back the suboptimal goal, DFS is not optimal. Now let's address the issue of completeness. So what happens is, in terms of a finite, this is a finite finite status space tree. So in terms of finite status space tree, DFS is complete. But in terms of a tree is infinite, like there is a loop or a cycle in a tree. Whenever there is a loop or a cycle into a tree, then it's called graph. Suppose it's a graph where there is a loop. Okay, so suppose we have another graph which is A, and there is a cycle. In this graph there is a cycle. So what will happen in terms of this graph? BFS will not be, it will never give you a proper solution. It will never reach out to the solution. This loop will be infinite. It will go back to one to another, like one node to another, and it will create an infinite loop, which is why DFS will never find a solution. So there will be no solution, no solution in terms of infinite loop. So this is what it is said, that DFS is not complete. So optimality issue has already been addressed. DFS tends to return the suboptimal goal of the goal node, and also the step cost is high. There is a formal definition regarding optimality. I will write that into the description box below, because I don't have space over here to write, and it would be time consuming again. So we have already addressed all the issues, like the space complexity, time complexity of DFS. Also we had came across to the simulation, stack based simulation of DFS, and also we got to know about the optimality and completeness in terms of DFS. And yeah, this is all from the tutorial and the discussion. And in our next discussion, we will make a comparison, like we'll give some advantages and disadvantages of BFS and DFS. Okay, because of the simplicity, we would understand it more properly, that the differences between DFS and BFS in our next tutorial. And what else we are going to learn is the limitations, like we have some limitations in DFS, how we are actually resolving this limitation of DFS. We will resolve it through two more searching algorithm. We will discuss about them on our next tutorial. For now, I will say you all goodbye, and I hope it was a fruitful and helpful discussion on DFS. And Please stay in touch, and please see the description box below, because I will write the definitions down. So thank you for now. Goodbye.